Hello everyone. Today we will be starting with galvanic cells, and this is part of the production of materials topic. In the first section of galvanic cells, we'll be learning about the composition, the components, and also the reactions that take place in a galvanic cell. So let us begin. A galvanic cell is known as a chemical reaction device, and this is because a chemical reaction takes place in a galvanic cell. And this chemical reaction is spontaneous, which means that it occurs not automatically and naturally. So in a galvanic cell, what happens is chemical energy is converted to electrical energy. And this is a very vital point because the chemical energy that is being used here is converted to electrical energy, and that's what's happening with the chemical reaction. It is also known as Voltaic cells. So for example, if you see Voltaic cell on an exam paper or a textbook, that simply means the same as a galvanic cell. So let us go into detail. Now, in a redox reaction, in a galvanic cell, a redox reaction takes place, which means that this a chemical reaction occurs in two parts. One is called the reduction half reaction, and the other is called the oxidation half reaction. Now, as you can see, the word redox comes from these two, red, ox. In reduction, the species would gain electrons, while in oxidation, the species would lose electrons. Now, if one species gains electron and the other loses electrons, there is an electron transfer. And that's exactly what is happening in a redox reaction. So to memorize this, because we need to know this for HSC, we have a little memorizing tool, and that's called oil rig. So where O stands for oxidation, is losing electrons. While the R from rig stands for reduction, is gaining electrons. So this way you can memorize this redox reaction. So I would recommend you to write this down because this is very important. So oxidation is losing electrons, while reduction is gaining electrons. Now, the two half cells are physically separated. Because oxidation and reduction are two reactions, they happen in two different half cells. What's a half cell? As you can see here in the diagram, there are two components. One has the anode and the other has a cathode. And they're physically separated yet connected by two different components here. Now let's go into detail. Electrons that are transferred travel through an external circuit. As I told you before, a redox reaction is a transfer of electrons. So these electrons that are transferred cannot move through a aqueous solution. What they do is they travel through an external circuit. It's wires and it's a wire circuit. Because the movement of electrons is electricity, so electricity is simply the movement of electrons, there's electricity being produced. And that's what happens in a galvanic cell. Usable electrical energy can be generated, and this is because of the movement of electrons. So the electrons that are transferred would produce the electrical energy. Now, there are components of a galvanic cell. The first component we'll be looking at is the anode. So here is the anode, as you can see, and this is the electrode where oxidation occurs. Now, if you review back to what we just did, what is oxidation? Oxidation is a losing of electrons. So this is where the electrons come from. So the anode electrode would give away electrons, as you can see. So the E with a little minus sign here indicates electrons, and the arrow pointing it going away from the anode. And this is a negative charge in the galvanic cell. So to mark this, we put a little minus sign next to the anode. Now the cathode is the other part, and the cathode is where reduction occurs. If you remember, reduction is a gaining of electrons. So the electron we lost from the anode is gained at the cathode. And this has a positive charge in the galvanic cell. So we put a little plus sign next to the cathode. Now to remember that the cathode is a plus, we just use the word cathode and it has a T. The T looks like a plus sign, therefore we can memorize it as the plus. And vice versa, anode is therefore the negative. Now the electrolyte. Electrolyte is a substance in solution or molten state that conducts electricity. So in this diagram, the electrolyte is this blue solution here. And an anode and the cathode, the electrolyte may differ. And that's why the electrolyte in the cathode-anode compartment is called the anolyte, while the electrolyte in the cathode compartment is called the catholyte. Also in this circuit, we have a salt bridge, as you can see here. The salt bridge connects the two solutions, and it completes the circuit. And it is usually made up of potassium nitrate. Now I want you to go back to year 11 where we learned about solubility rules, and we learned that potassium salts are always soluble, and also that nitrate salts are also always soluble. Now this is a key component, because that means when you're transferring ions, they will not form precipitates when they're transferring other ions. So for example, if you're transferring cations, the cations would bond with the nitrate here. But since nitrates are always insoluble, they will not form precipitates. And this is very important for the salt bridge. This maintains the electrical neutrality of the half-cell solution by allowing ion migration. So ions would migrate along the salt bridge. Now we'll take an example of a galvanic cell, and one is the Daniell cell. So the reaction happens between zinc and copper sulfate. The anode in this cell is a zinc. Now how do we know that? Now anode is where oxidation occurs. So oxidation is the losing of electrons. Now losing of electrons, the more reactive metal would lose more electrons easily. This is something you learned in junior school, that a reactive metal would easily lose electrons. So which one is more reactive? For this to be figured out, you look at the standard potentials table, which is at the back of your periodic table. And here you can see that zinc is above copper. That means zinc is more reactive. So zinc is going to be the anode. Therefore, the anolyte is zinc sulfate, as you can see. So that means zinc 2 plus ions and sulfate 2 minus ions are going to be in this solution. The cathode is copper, and copper is where the reduction would take place. That means gaining of electrons. So the catholyte is copper sulfate, and again you would have copper cations and sulfate anions. The salt bridge, made up of potassium nitrate, is going to allow ion transfer. Now we'll look at the oxidation reactions and the reduction reactions in a greater depth. So the oxidation happens at the zinc anode, and the zinc anode is where you lose electrons. So here zinc would lose 2 electrons to produce a zinc cation. Now it produces 2 electrons because it has 2 valence electrons. So that's why it produces 2 electrons. And it is important to balance the charges. So in this side of the equation, this charge is 0 because it's only the element. But then here, the cation has a charge of +2, and here the electron has a charge of 1, -1. But since there are 2 of the electrons, the charge is going to be -2. If you combine these together, you would get 0. So here the charges are balanced, and it is always important to balance the charges. That way you can balance the equation and also make sure that your answer is correct. The reduction reaction at the copper cathode. So what happens is that zinc loses an electron, and these electrons that zinc loses are going to be gained by the copper ions. So the copper cation would gain 2 electrons to form copper. Again, always balance your charges. 2 plus, and we have 2 electrons, therefore going to be 2 minus. And that's going to give us 0, and there's going to be 0 here. Now the net ionic equation. Now this is oxidation and reduction reaction, but this is going to be our redox reaction. With our redox reaction, what we simply do is we add these together. So if we add these together, we add them down. So we have zinc plus copper, we add it together. But here we have the 2 electrons. The 2 electrons are being given off here, but then it's going to be taken in here. That means they are being used. So you don't have to worry about them when you're writing your net ionic equation. So on this side of the equation, there's going to be zinc, the solid, which is a metal, and we have the copper cations reacting to form zinc cations and our copper metal. Now what we have is the zinc, and what really happens here is a zinc anode dissolves and we have copper forming. Now let's just go through this. As we went through, zinc would lose electrons. So it forms zinc 2 plus 2 electrons. So zinc, the metal, is gonna eventually dissolve and form this. But at the same time, the copper would gain electrons. So the copper ions from this catholyte will gain electrons. So the copper ions plus the 2 electrons we got from the zinc is going to form copper metal, and this black stuff is a copper metal. So the blue color of the copper sulfate will fade. Why is that? Because the copper sulfate has copper ions in it. As they get used up, the blue color in the copper sulfate would eventually fade. The voltage gradually decreases as the reactants near depletion. So as we have all the zinc being used up, there's going to be less electrons being transferred. As a result, the voltage is going to be less. Electrical neutrality maintained by migration of ions, and that is because of the salt bridge. So the salt bridge provides a medium for the ions to travel through. So we have zinc ions moving into the salt bridge and the potassium ions moving into this copper cathode half cell. So the zinc ions are found here and they are moving in to the salt bridge. And the copper ions, which are in the salt bridge, are being pushed out. So we have copper ions from there being pushed out that way. But the sulfate from the catholyte moves into the salt bridge and the nitrate moves into the zinc anode half cell. So we have sulfates here and they are being moved in to the salt bridge. As a result, the nitrates from the salt bridge are being moved out. And this is what happens in a galvanic cell. Now moving on to galvanic cells with gases as reactants. Now what we looked at was solids, electrodes with solids. Now what happens when there are gases as reactants? We still do require an electrode, and these electrodes are going to be inert substances such as platinum or titanium. Why do we use inert substances? Because inert substances don't react, which means that they don't partake in the chemical reaction. So for example, here we have used electrodes, a platinum electrode, and the gas that's going to be reacting is going to be hydrogen gas. So the reactant gas is bubbled over the surface of the electrode. So that's for the reaction to occur. It's going to be bubbled into the platinum electrode. Energy conversion in galvanic cells. Chemical energy stored in the electrodes before chemical reaction converts it into electrical energy. So clearly there is an energy conversion from chemical energy to electrical energy, and that is what you have to know about galvanic cells and energy conversion. Usable electrical energy takes the form of an electrical current that flows from the anode to the cathode via the external circuit, and this is the movement of electrons as we talked about before. Powers electronic devices. Now, what are galvanic cells used for? Well, they are used in electronic devices and batteries, and we'll be learning about this later on in the topic. Now, if we look at the shorthand notation for galvanic cells, because galvanic cells are not always going to be drawn for us, they're going to be a shorthand version. And you would see this in HSC papers as well as textbooks, and it's really important to know it. So, for example, you would first write the anode. You will write the state down, and you will show the difference with a little line going across. Then you would write the anolyte, and again writing the state. Now this is one of our half cells, and the other half cell is this part. To separate the half cells, you use two lines going down. On this side, you would write the catholyte first, and you would write the state again. You would separate them using a line, and you would state the cathode again with the states. Now we'll take the Daniell cell for example to make this much more clearer. For example, in the Daniell cell, the anode is zinc, and the anolyte is the zinc ions. In the next half cell, there's going to be copper ions, which is the catholyte, and also the copper metal, which is the cathode. So as you can see, we have learned quite a lot for now. We learned about the composition of a galvanic cell, also the components, and also what happens in a galvanic cell. That means the redox reaction, the reduction, and the oxidation reactions that are going to take part in the reaction. So now we'll be looking at questions that might be asked from this section. Question 1. In the galvanic cell, electrons are produced at. So here we have 4 options. We'll consider each option one by one. Option A. The copper electrode, because copper is more active than zinc. If you refer to your standard potentials table, you would realize that zinc is above copper, which means that zinc is more reactive than copper. Since zinc is more reactive than copper, the statement A is incorrect. We'll move to statement B now. The copper electrode, because copper is less active than zinc. Even though the statement copper is less active than zinc is correct, we should always look at the question. Electrons are produced at, which means that electrons are being lost. And oxidation is a reaction in which electrons are lost. And electrons are lost at the anode, which is a more reactive metal. So electrons are produced at the more reactive metal, and the more active metal here is zinc. So option B is incorrect. Moving to option D now. Both electrodes, because zinc and copper are both more active than silver. Silver is not taking part in the reaction. One, it is not mentioned in the galvanic cell, and also it's an inert metal, which means that it's not going to be reacting. So option D is incorrect. Now looking at option C, the zinc electrode, because zinc is more active than copper. Since zinc is the anode, oxidation takes place at the zinc. and oxidation is the production of electrons. So C is the answer. Now we'll move to question 2. In the galvanic cell, electrons flow from the zinc electrode to the copper electrode. What does this tell us? Again, we have 4 options. Option A, zinc is more active than copper. This is a true statement because zinc is more active than copper. So even though this is true, we should always consider all our options. Now we'll move to option B. Zinc metal is undergoing oxidation. Again, true fact, because zinc is the anode because it's more reactive and oxidation happens at the anode. Therefore, it is losing electrons and option B is correct. We'll consider option C. Option C says the zinc electrode is the anode. Zinc is undergoing oxidation, therefore it is the anode. And this is again the true statement. So all these 3 statements are correct. Now consider option D, all of the above, which means that all these statements are correct. Therefore, option D is the answer. So as you can see, if you have a question like this, it is vital to always consider all your options. Always read through all the options before writing your answer down, because you might get incorrect answers if you just chose A after reading the first statement. Now moving to question 3. Question 3 has a diagram in the question. In this diagram, which of the following would be called an electrolyte? Now we know an electrolyte is the aqueous solution that allows ion movements. So is it option A, which is the copper anode? The copper anode is a copper metal where oxidation takes place. And here is a copper anode. So copper anode is not the electrolyte. Option B, the salt bridge. The salt bridge acts as a medium for ion flow, completing the circuit. In this case, the salt bridge is here and it is not the electrolyte. Voltmeter is option C. The voltmeter reads the electron flow through the circuit. So here is a voltmeter and it is not the electrolyte. Option D, silver nitrate solution. The silver nitrate solution does act as an electrolyte, conducting electricity. Therefore, option D is the answer. So in this case, we have 2 electrolytes. One is copper sulfate and one is silver nitrate. And silver nitrate is given as an answer here, even though copper sulfate is not. And so therefore, we choose silver nitrate as the answer. Now we move on to question 4. Question 4 is a question asking, explain why a salt bridge or porous barrier is used in the connection of 2 half cells. Now again, we have a key verb here which says explain. So you have to really give a detailed answer and explain why. Not just defining its purpose, but also say why it is used that way. So the salt bridge allows anions and cations to migrate between each half cell. This is going to be part of your answer, and this is going to be called part 1, where you're really stating the function of a salt bridge. So it allows anions and cations to migrate between each half cell. In this section, the migration of ions are important to maintain the electrical neutrality of the half cells. Here we're explaining how they work. So it is to maintain the electrical neutrality of the half cells. And this, without the salt bridge, which is now stating why we use it, the circuit of the charged particles through the galvanic cell will not complete the redox reaction. So it is to complete the reaction. And this step by step shows why a salt bridge is used to connect the 2 half cells. So that is the kind of answer you'll be looking for this question, and it says explain. So you really have to give a detailed answer for that. Now we'll go to question 5. Question 5 is true and false, and this might come in the HSC, and most certainly in your examinations at school you would find these kind of questions. There are 4 parts: A, B and C and D. So A, oxidation reduction reactions in galvanic cells generate electricity and some heat. Yeah, we do know that they generate electricity, but during the conversion of chemical energy to electrical energy, some of the energy may also be converted to heat energy. Therefore, the statement is true. Now B, in galvanic cells, electrons flow through the external circuit between the two half cells. We know that electrons are being transferred in a galvanic cell because the redox reaction is an electron transfer reaction. So the electrons that are produced at the anode are being transferred to the cathode using an external circuit. So this is also a true statement. The half reaction of the oxidation of copper in a galvanic cell is, and they have given us a chemical equation here. Now here, copper cations are gaining 2 electrons to give us copper, but it's oxidation. Oxidation is a losing of electrons. Remember back to oil rig. So oxidation is losing of electrons, but in this case they're gaining electrons. So clearly this is a reduction reaction, not an oxidation reaction. So therefore this statement is false. D. To ensure reliability when comparing the voltage of different galvanic cells, all electrolytes should have the same concentration. Now this is a condition for galvanic cells, and to ensure reliability they should always have the same concentration. So therefore this is a true statement. Now in this section we covered the composition, the components, and also the reactions in a galvanic cell.